sort of classify the different weighted residual schemes, so depending on the choice of the arbitrary functions, the del ui's, we arrive at the different weighted residual methods. So if we choose del ui such that del ui is equal to phi. So if I choose, I didn't do this in that case, right? The phis were, c1 x squared minus 2, they were arbitrary functions, and then the del u's were 1 and x, right? So in the case that the example we just worked, I did not choose them to be this way. But if I were to have chosen it that way, I get what's called a Galerkin method. And up to now, I haven't given it a name. I've just said this arbitrary function. In the literature on finite elements, this is often called a test function. So if you hear me say going forward, the test function, I'm talking about that del ui. Okay. If I choose the test function to not be the basis functions, then I get what's called a Petrov-Galerkin method. And that's effectively what we did. If I choose the test function to be equal to essentially the right-hand side, with the right-hand side with the approximation space plugged in, then I get what's called a least squares method. If I choose the del ui to be equal to the delta function, I get what's called a collocation method. So where delta is the Dirac delta function. So of the methods above, in terms of weighted residual methods, of the methods above, only the least squares method results in a symmetric coefficient matrix. So I didn't write it down when I solved for the C's, but if I would have, what it would have been was this. I just showed you the answer. Why do we care about symmetric coefficient matrices? Speak up.
Do I have a unique answer? Or?
No, no. This is not symmetric. It has a unique answer. Yeah. I mean, solve time by meaning is the sense that we ultimately we're not just going to solve tiny problems like this. We're going to solve big problems, right? And big problems, if the matrix is symmetric, it turns out they're also going to be very sparse, right? And so, meaning there's going to be lots of zeros in here. Typically, when we have sparse matrices, what type of numerical solvers do we use? Do we use direct solvers, like Gauss-Seidel, or do we use an iterative method if it's sparse? Lots of zeros in there. What do you use? Use iterative solvers, right? You typically don't use direct solvers when there's lots of zeros in there. Iterative solvers lend themselves well to sparse matrices. What's the most popular iterative solver? Conjugate gradient. You use Trulino, so of course you're going to say GMRS. But no, the most popular one is the conjugate gradient method. And the conjugate gradient method only works on SPD, right? Symmetric positive definite matrices. Okay? So the reason we like symmetric matrices is actually twofold. One, they lend themselves nicely to iterative solvers, specifically the conjugate gradient method, and you get fast convergence. The other thing is storage, right? A symmetric matrix, we don't really have to store. We don't, a smart storage system on a computer for a big symmetric matrix, you wouldn't store the lower half. Right? So you basically cut your memory footprint in half if your matrix is symmetric. Okay? Now sometimes, as we'll see even in this class when it comes to polar elasticity, sometimes the physics just you can never get a symmetric matrix. Okay, but in this case for this ODE, it's our choice of approximation can give us a symmetric matrix or not. Okay, so.
But this matrix is not symmetric, right?
I said it's not symmetric. I wrote it down. It's not symmetric because we effectively used the Petrov-Galerkin method, right? I didn't when I chose my phis and my test functions, my basis functions, my test functions. When I chose them, they weren't equal to one another, right? So we want a method. We want a method that'll give us a symmetric matrix.